This is SpaceTime, Series 28, Episode 42, for broadcast on the 7th of April 2025. Coming up on SpaceTime, another clue helping to pry open the door to the antimatter universe, a new technique to try and detect dark matter, and what caused the Spectrum rocket to fail. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Physicists have discovered a fundamental difference in the decay behaviours of ordinary matter particles and their antimatter counterparts. This discrepancy is important because it could help bring scientists a step closer to understanding how everything in the universe came to be. The findings by the LHCb detector at the Large Hadron Collider reveals a significant difference in decay rates between the ordinary matter and antimatter versions of the beauty lambda baryon. Lambda baryons are a family of subatomic hadron particles containing an up quark, a down quark, and a third quark from a higher flavor generation, in this case a bottom or beauty quark. Quarks are elementary subatomic particles and fundamental constituents of matter. They're found inside larger particles like protons and neutrons, which are the components of atomic nuclei. Quarks come in 6 types known as flavors. These are the up, down, top, bottom or beauty, charm and strange. The up and down quarks have the lowest masses, and heavier quarks rapidly change into up and down quarks through a process of particle decay. The authors studied the decay of a lambda B baryon into a proton and 3 mesons, which are particles containing a quark and an antiquark. In this case, the 3 mesons consisted of a kaon and 2 pions. The authors found the rate of decay was slightly different compared to that of its antimatter counterpart. Now, the probability of a significant discrepancy in decay rates between the ordinary matter and antimatter versions, the beauty lambda baryon, occurring just by chance, are calculated to be less than 1 in 3 million. In other words, this is the first result to cross a key statistical threshold for a discovery in physics known as 5 sigma. The findings, reported on the pre-press physics website archive.org, are based on an analysis of data collected by the LHCb detector between 2009 and 2018. It aligns with predictions from the Standard Model of Particle Physics, the foundation stone for science's understanding of the universe. And it offers a potential clue to the long-standing cosmic mystery of why the cosmos contains more matter than antimatter. See, the Standard Model suggests that antimatter is the same as ordinary matter, but with opposite charge, parity, and time. So, the antimatter equivalent of the positively charged proton is the negatively charged antiproton, and the antimatter counterpart to the negatively charged electron is the positively charged positron. The Standard Model also suggests that equal amounts of each were created during the birth of the universe in the Big Bang 13.8 billion years ago. The trouble is, we know ordinary matter and antimatter annihilate each other once they come into contact. And that means the universe should have disappeared in a blast of purple gamma radiation virtually as soon as it formed, and this clearly didn't happen. Now, antimatter does occur through natural processes like cosmic ray collisions and some types of radioactive decay, but only a tiny fraction of these have successfully been bound together in experiments to form antiatoms. Minuscule numbers of antiparticles can be generated in particle accelerators, but total artificial antimatter production has so far only ever achieved a few nanograms. So, for some as yet unknown reason, we live in a universe dominated by ordinary matter, with antimatter only ever appearing very fleetingly before being annihilated. But some particles disobey this matter-antimatter symmetry. It's a phenomenon known as charge parity or CP violation. Previously, scientists have only ever seen CP violation in mesons. Therefore, there's got to be some additional fundamental unknown differences between ordinary matter and antimatter, which has allowed ordinary matter to come to dominate the cosmos. And knowing this explains why we're here. The Large Hadron Collider, or LHC, is located at CERN, the European Organisation for Nuclear Research. It's a 27-kilometre long ring buried roughly 100 metres beneath the Franco-Swiss border near Geneva. The LHC includes 4 massive underground caverns, which house 4 primary detectors known as Atlas, ALICE, CMS and LHCb. Packets of protons, or other subatomic particles, are accelerated to within 99.9999% the speed of light in opposite directions in two particle beamlines around the ring, guided by cryogenically cooled superconducting magnets. And the beamlines intersect at any of these four detectors, colliding the particle packets at up to 13 tera-electron volts, in the process creating the sorts of conditions, pressures and temperatures that occurred just after the Big Bang. This is SpaceTime. Still to come, a new technique to detect dark matter, and we look at the possible causes for the Spectrum rocket failure last week. All that and more still to come on SpaceTime. Scientists have developed a new innovative approach to try and uncover the secrets of dark matter using atomic clocks and cavity-stabilized lasers. Dark matter is a mysterious invisible substance which makes up about 80% of all matter in the universe. Trouble is, scientists have no idea what it is. They know it exists because they can see its gravitational interaction with normal, so-called baryonic matter. That's the stuff that stars, planets, trees, cars, houses, dogs, cats and people are made from. One of the study's authors, Ashley Cadell from the University of Queensland, says that despite many theories and experiments, scientists are yet to understand dark matter. Cadell says her new study, reported in the journal Physical Review Letters, uses a different approach, analysing the data from a network of ultra-stable lasers connected by optical fibre cables, as well as from two atomic clocks aboard GPS satellites. She says in this case, dark matter is acting like a wave because its mass is extremely low. So Cadell and colleagues used the separator clocks to try and measure changes in the wave, which would look like the clocks displaying different times or ticking at slightly different rates. And this effect gets stronger as the clocks are further apart. The authors were able to search for forms of dark matter that had been invisible in previous searches because it emits no light or energy. I mean, we still don't know what it is, but at least we can see what it's doing. She says that by comparing precision measurements across vast distances, the team could identify the subtle effects of oscillating dark matter fields that would otherwise cancel themselves out in conventional setups. They were able to search for signals from dark matter models that interact universally with all atoms, something that's eluded traditional experiments. Cadell says the research means scientists will now be able to investigate a broader range of dark matter scenarios, and perhaps even answer some very fundamental questions about the fabric of the universe.
So there have been quite a lot of experiments, to be honest. For a while, the type of dark matter that everyone was looking for was called WIMPs, so it's weakly interacting massive particles. And the way that you look for those is similar to the way that the older neutrino detector experiments work. So the basic idea is you can't see dark matter, you can't hear it or anything like that. But it's sort of the same idea as if you literally couldn't see anything, you're just kind of feeling around in the dark and waiting for something to hit you. It's pretty much the same idea for the experiments, right? So for the neutrino ones and also for the newer dark matter ones, what they do is just get kind of just a big vat of liquid or a gas or even both sometimes, and they just wait for things to hit it. It's quite literally you can't see anything, so just sit and wait, and if anything hits it, then it might give you a little bit of light.
You got photoreceptors which then pick that up.
Yes, yeah, exactly. Usually you have a big array of photodetectors on the top and bottom of these things, and if you get that little bit of light, it goes, oh, that was a photon. So that's a detection. But unfortunately, none of those have really found anything so far anyway. They kind of just keep building better and better ones because it could just be that we're just missing it or it's just not sensitive enough yet. So there have been some other really cool experiments as well, such as if you're looking for axions, you make this thing called a helioscope or a haloscope, and it's sort of a similar principle, but it's a little bit more complicated. So axions, they do a very odd thing where if they're exposed to I think a magnetic field or an electric field, then you can see it. But a lot of there are so many experiments, to be honest. People are very creative in this field.
Because the problem with axions is we still don't know whether they're real or not.
Yeah, that's the problem with most of these particles, to be honest. We do just kind of keep coming up with new dark matter models and trying to think up experiments for them. It's a very very creative field, to be honest, but it is quite difficult.
And the problem is we know dark matter's real because we can see its influence on regular baryonic matter. So
exactly.
It affects the way galaxies revolve. It affects the way we can see more distant objects through gravitational lensing. And that raises an interesting point. Because it has gravity, it must have mass, and we know that mass slows down time.
Yeah, exactly. So it's seen pretty much only through its effects through gravity. So, we don't see it in any telescopes, no matter what wavelength we're looking at. We only ever see it through how it affects other things. And it's basically just galaxy glue, right? So if we didn't have any dark matter, all of our spiral galaxies would just kind of be ripped apart because they seem to be moving rotating a lot faster than they should be for how many stars we can see in there. So without dark matter, it's all a bit of a mess.
This is where your research comes in.
Yeah, so we were kind of thinking in a little bit of a different range than the usual dark matter experiments. So people have been looking more towards some more interesting models in the last couple of years. So people have been looking, because the WIMP models are usually quite high mass, everyone's been sort of going down to the opposite mass scale. So we were looking at ultralight dark matter, which is so lightweight that it starts to behave more like a wave than a particle, because with really lightweight particles, you have to still match the amount of dark matter that we know is in the universe. So if it's really lightweight, that means there has to be way more of it. And so we kind of just get sort of, I think of it as kind of like a mesh over the entire universe that just has like little waves in it. But to look for that is a little bit interesting. So there are quite a few experiments using atomic clocks and stuff. So what we were trying to do was essentially see if we could try to detect dark matter with two separated atomic clocks. And what's cool about this is those already exist. So there's a big fibre network in all of Europe. So it starts in London at the National Physics Lab, and it goes all the way to PTB in Germany. And with that, there's atomic clocks at each point along there, and a couple of them. But the important ones are at the start and the end, because that's where you get the maximum separation, so biggest distance between them. But what's cool also is that you probably know that there's atomic clocks on GPS satellites. Now, they're not quite as accurate as the ones that NPL and PTB have, but they are massive distances apart. So we were trying to basically use these clocks to check if there was any ultralight dark matter, because what it would look like is just these two clocks ticking at a different rate or just having a different time displayed on them. So if there was a difference in that, then it could be that dark matter was interacting with the atoms in these atomic clocks.
And what's happened so far?
What's happened so far is that we didn't see anything, which pretty much is kind of the state of dark matter research, is trying to figure out what dark matter isn't. So you might have heard of people saying constraints a lot. And constraints just means we've kind of tightened the area that we're looking for with dark matter. And we were looking for a slightly different coupling, so a different type of interaction this time. So we've got newer constraints on this type of interaction, which is really quite cool, because it just means that we're looking at a slightly different model to what you usually search for. So unfortunately, I can report that we haven't detected dark matter. But what's actually really cool about this experiment is that it would be really useful in the case where dark matter is already detected. So what's nice about having massively spatially separated atomic clocks is that you actually end up sensitive to spatial distribution of dark matter, which means that we know that dark matter exists, but we don't actually know how it's distributed throughout any of the galaxies, right? So we don't know if it's, if it clumps together. We don't know if it's just completely uniformly spread out. And what's really nice is that when you have an experiment that is both separated in space and time, you can actually probe those differences. So you can try to work out what the spatial distribution is, which would be useful in the case of, say, we had a terrestrial detection of dark matter, but we want some more information. We can then use these separated atomic clocks to figure out what that dark matter distribution actually looks like, which is really quite cool in my opinion.
Because that's one of the problems. We don't know whether it's part of the actual fabric of space-time or whether it's just in big clumps, and that's where galaxies then form.
Yeah, exactly. There's a lot of research into large-scale structure, and it seems to be that where dark matter forms on large scales is exactly where the galaxies end up. But the problem is we don't know the small-scale structure stuff, so how it settles in a galaxy. We know that it settles where galaxies are, so we will get a massive clump of dark matter, and then the galaxy will form on top of that. But how it's actually distributed when you look in way, way closer inside the galaxy is more of a mystery. There's a lot of theories, and some people just kind of make assumptions to go with the most popular one, but it is kind of an interesting field to really look into.
Yeah, because some of the observations have been counterintuitive too, haven't they? For a while there was a lot of talk about dark matter is more dominant in dwarf galaxies, and yet when we look at dwarf galaxies, some of them seem to be very bereft of dark matter.
Yeah, they're honestly, I usually look at like spiral galaxy stuff, so I'm not the expert on different types of galaxies, that's for sure. But I do know that at least when I was doing a lot of my undergrad, they teach us about different types of galaxies. And there was one that I didn't really expect, was that ellipsoid galaxies, or like some types are just like almost entirely dark matter, which was a little bit insane to me.
So what's happening next? Where do we take this?
Well, I mean, that's a good question. There are basically just more atomic clocks to make. Like the more accurate that you get an atomic clock, the better it will be at detecting these things. So like atomic clocks are already extremely accurate. If you know much about like the watch industry, like quartz watches were kind of a big thing because they only lose like 1 second every couple of months or couple of years if it's a really good one. But the current atomic clocks, the ones that are the best, if they had been made at like the Big Bang at the start of the universe, they wouldn't have lost a second yet, which is really quite amazing. So that affords a lot of accuracy, but we can actually make them better. If it just continues on, atomic clocks are going to get much, much better. And when you have way more precise equipment, it's just going to make the experiment better itself. So the next stage, I guess, would be with 1, a better atomic clock, and 2, even more spatially separated. So what was something quite cool that we found in our experiment was that the signal strength actually was directly proportional to the distance between clocks, which means that you can just scale this experiment up further and further by moving those clocks further and further apart.
That's Ashley Cadell from the University of Queensland. And this is SpaceTime. Still to come, we look at what could have caused the Spectrum rocket failure. And later in the science report, a new study shows that the Southern Ocean's warming may be affecting rainfall and drought conditions in the tropics. All that and more still to come on SpaceTime. Investigators are working to try and determine the cause of last week's launch failure of a Spectrum rocket. The Spectrum was launched from the Andøya spaceport on Norway's northwestern coast on what should have been the first ever orbital rocket launch from mainland Europe. The 28-metre tall two-stage launch vehicle, built by German company ISA Aerospace, was on its first test flight. The launch is designed to carry up to 1,000 kilograms into low Earth orbit and 700 kilos into sun-synchronous polar orbits. But there was no payload on this first test flight. Now, as we've said previously on the show, space is hard. So, while the investigation's continuing, let's speculate as to what's likely to have gone wrong. After watching the launch repeatedly, both in regular and slow-mo speeds, we can see that the rocket was already experiencing thrust vectoring oscillations from shortly after its launch. And those oscillations appear to amplify as the engine's gimbaled during the ascent rollover manoeuvre some 18 seconds after liftoff. In fact, if you look closely, the oscillations appear to be generating a self-perpetuating amplifying loop, increasing the problem and eventually leading to the vehicle tumbling and veering sideways out of control at an altitude of around 500 metres. Now, at this point, mission managers terminated engine power. There was no overall self-destruct system. By terminating engine power, it allowed the rocket to plummet back down and into the sea. Now, the rocket didn't actually explode in the sky. It only detonated once it hit the water. Now, all this suggests some type of issue with the sensor inputs from the guidance system to the gimbals, which were then amplified during the rollover manoeuvre. Well, at least that's what it looks like. Needless to say, we'll know more in the weeks to come. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. There are new warnings today that the Southern Ocean's warming may have a more dramatic effect on rainfall and drought in the tropics than warming from the Arctic Ocean. The findings, reported in the journal Nature Communications, are based on computer simulation climate models. While Arctic warming has been studied extensively, the Southern Ocean has been warming more slowly and is less well understood. The authors found that just 1 degree Celsius of Southern Ocean warming could affect tropical rainfall to the same extent as 1.5 degrees Celsius of Arctic Ocean warming. The authors also investigated the effects of Southern Ocean warming on specific tropical regions, finding that it could increase rainfall in northeastern Brazil while making drought risk worse in the Sahel region of sub-Saharan Africa. Scientists have developed the world's smallest temporary pacemaker. A report in the journal Nature claims the device, which is smaller than a grain of rice, was capable of regulating a heartbeat during tests of its effectiveness in human heart tissue. The tiny pacemaker incorporates electrodes that generate an electrical current when exposed to body fluids. That eliminates the need for an external power source or lead wires and reduces the risks that come with external power supplies and invasive surgery. Once no longer required, the device simply breaks down and is absorbed by the body. The authors say this offers a safer alternative for smaller body sizes or for those who may not be able to handle invasive surgery, such as fragile newborns with heart defects. Researchers have discovered that miso made in space has a nuttier, more roasted flavour than when it's made on the Earth's surface. The findings, reported in the journal iScience, are based on a study which sent a small container of fermenting soybeans and salt, they're the ingredients of the traditional Japanese condiment miso, to the International Space Station. The ingredients then spent 30 days fermenting in space before being returned to Earth, and it was then compared to 2 batches of miso made at the same time on the ground. Analysis found that the space miso fermented successfully, but that there were notable differences in the bacterial communities present in the misos, and that the space fermented miso had a more roasted nutty flavour than the Earth miso, while still maintaining its classic salty umami flavour that people know and love. There's a growing trend in some parts of Indian culture promoting the consumption of bovine urine and faeces as a form of alternative medicine for medicinal purposes. The problem is there's no scientific evidence to support claims that consuming these items has any beneficial effect. In fact, the research suggests that it can introduce dangerous bugs, toxins and other harmful substances, potentially causing infections, especially antibiotic-resistant bacteria. Tim Mendham from Australian Skeptics says that despite the dangers, this practice is being strongly promoted by some dubious academics and politicians.
India's got a lot of alternative medicines, things that are sort of quite embedded in society. Ayurveda medicine is basically the herbal alternative medicine of India. It's got a lot of different aspects to it. And it's actually often endorsed by the World Health Organization. The director of the Indian Institute of Technology in Madras has been saying that he drinks cow urine and that it can cure ailments like fever and irritable bowel syndrome. In fact, they take it even further and say it can cure a whole range of different conditions. The trouble with cow urine, it's got a lot of impurities in it. It's probably got E. coli in it, which can cause you a lot of problems, starting with diarrhea and getting worse from there. But they also say cow dung, you mix a bit of cow urine and cow dung pats, mix it up together, and that can cause all sorts of disease. There are things in cow dung because there's often larvae in there, of tapeworms and that sort of stuff, and you're swallowing cow dung, yes, he's probably swallowing those as well. So it's not going to do your body any good. It probably can actually do your body major harm, your brain, your muscles, your eyes, all sorts of things. But this has been endorsed by at least one director of a university, and it's also endorsed by a lot of political leaders who are not necessarily medically trained or even medically literate. But politicians within the Indian government, a lot of them are promoting Ayurveda. It's almost like being seen as an alternative to traditional Chinese medicine. They're trying to get market share, in other words. There's a group called the Doctors Association for Social Equality, and there are other sort of doctors groups who are actually campaigning actively to say, stop doing this. It is dangerous that you are promoting this out there treatment for medical conditions, which is purely based on some sort of spiritual healing techniques that have no bearing, that don't work. Sorry, Ayurveda, sorry, sort of Indian population, a lot of people sort of swear by it, but these things are not only won't help you, they very well might harm you. And that's the thing. E. coli will cause all sorts of things. These larvae will cause all sorts of things. Drinking cow urine, chowing down on a cow pad is not advised.
That's Tim Mendham from Australian Skeptics. that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.